Continuing with STM Tech BMS Battery Management System, Part 2. As I mentioned in my previous video, that basically we're going to be using STM32 microcontroller with the analog devices components. We're going to be using an LTC6820 for the ISO SPI protocol, and that will be connecting the master BMS with the slave BMS, and also it will be connecting other slaves in case we have like a large battery. And we're going to be using also the LTC6813 chip to connect the battery cells to the slave BMS. So let's look at the tools we're going to be using for this project. We'll be using the STM32 Cube MX IDE. This is how we're going to configure the pins, and we're going to configure our clock. As you will see that the STM32 use like 4 type of clocks: low speed internal oscillator, low speed external oscillator, high speed internal oscillator, and high speed external oscillator. So there are 4 type of clocks that we're going to be using. We're going to be using also KiCad for the creating schematic and PC board. And finally, we'll be using the GLC PCB to assemble and create our PC board. So let's look at the first, let's look at the STM32 Cube MX IDE. We're just going to go briefly how this tool can help us configure the pins and the clock for our STM32 microcontroller. And also we're going to be using this configuration, and we're going to create a C code as you see here. And that's going to be basically that initial configuration is going to be created by this tool that I mentioned, the STM32 Cube MX. So you can, there are 2 ways for configuring pins. You can either click on specific pin, for example, and so for this one it's configured to be GPIO output. So if I go here, for example, and reset the state, it's gone. But if you want to just configure this way, you just can go to the click on the pin, and then just create click on the option you want, either inputs, GPIO, inputs, outputs, or any other protocol. So for right now, we selected this pin here to be as a GPIO output, and actually this one is connected to an LED. So if you want to just create a label, I can just call it, for example, test_LED. So I'm going to have this pin connected to an LED just to basically for testing purpose. Okay, the same thing here. So let's say this microcontroller, we are not going to be using the internal clock. Let's say we're going to be using, for more precision, we're going to be using an external clock. So you can either through here, just like we did with the you go and click on specific pin. If I click on pin, I see what are the options available to me. Or I can go to the left hand side here, and for example, if I go, let's say, to connectivity, okay, if I decided, for example, I want to use SPI, since we're using SPI, since we already have SPI1 right here, let me select another SPI. So for example, I selected a second SPI. I go and enable it here. Let's do full duplex master. Here we have basically these 3 pins being added here. SPI2 for clock, the MOSI and MESO. So I'm just gonna go and disable it, but basically this is the way how you can configure the pins. When you want to configure the clock, so the STM32 Cube MX give you flexibility to this graphical user interface to configure your pins, but it's very flexible, and it gives you also options of how you can configure the clock basically. So let's say you want to use a different speed for your clock. Let's say you want a 64 here megahertz. When you enter, everything is going to be calculated for you, and all these prescalers going to be set up to give you a system clock of 64 megahertz. So I'm just going to keep it -6 here. Everything is going to be calculated again, and you don't have to do anything. I'm just going to go over the slides to explain you how this clock actually is configured. So the same screenshot of the XPX of the STM32 Cube MX IDE on the clock configuration. So this clock, it might look like a little bit intimidating, but I'm just going to break it to you into parts. So we have exterior clock. That's when you want to use an external oscillator or clock basically, because as you know, the clock used with the STM32 is not very precise, and just in case you need like with a high precision, you can pick your own. So once you use an exterior clock, then you're going to be basically specifying what is the input frequency. So for example, the one we choose operate at 16 megahertz. You have a range between 4 and 26 megahertz, so I choose 16 megahertz. All these parts here are for the interior clock, okay? So I'm going to break this diagram or this tree diagram into parts. So the top left corner is for the RTC clock. Basically, this is for like a real-time clock when you want to have events and providing some kind of day calendar for specific purpose. You can actually either use an external clock or just use the internal clock. So right now we just kept the internal clock. So this RTC or the entire clock system use 4 type of clocks. As I mentioned in the slide, it uses a low speed exterior clock, low speed internal clock. These are like input to this RTC clock multiplexer, and based on your selection, either we're going to have an external one. If we have an external one, then it's going to be connected through here and it's going to come through here, or as in this project, we're using an internal clock oscillator, which using a speed of 32.768 kilohertz. Okay, so that's the RTC clock, just in case you want to use the RTC clock that comes with the microcontroller. And also this part here represents system clock. Okay, so that system clock either comes from an internal clock, so high speed internal clock. So basically it will be using 16 megahertz clock here, or in our case we are using the external one. So the clock information is going to come through here, and then we are using a phase lock loop basically to come up with all kind of frequencies that we want, that we desire. So it has this kind of a pre-scaler. It's basically nothing but dividers and multipliers to come up with the specific frequency. Okay, so that's another part of your microcontroller clock configuration. For specific, for example, as I will show you, for specific frequency, you put that frequency that you need, and then once you enter, this tool or graphical user interface, it's going to set up everything internally to have that specific frequency. And the good thing about this, the code is going to be generated for you. You don't have to do anything, as long as you gave the tool the input frequency and the desired frequency. You enter and you should be set, and of course everything is going to be calculated for you, including the peripheral clocks. The bottom one is if you want to basically this is a microcontroller clock output for specific if you want to set specific pin to have a specific clock output, you can use this. We're not, it's everything as you see, it's grayed out, so we're not using that. And for every microcontroller device, you're going to have a different setup, but this is basically the main you know, how you set up the clock configuration. Now let's go back. I just want to show you something. Let's go back to the IDE itself, that graphical user interface. So for example, if I wanna if I choose 60 megahertz, for example, if I wanna lower system clock, let's say I wanna 64 megahertz. If I enter, everything is gonna be calculated for me, and everything is changed here, including the prescaler multipliers. So if I just go back to 96 megahertz, and everything is calculated. And the good thing, that's all you have to do. I mean, for the initial configuration, you are already set. Everything is set up, the initial values, default values, the whole library, everything is basically set for you here. You just have to go and, you know, complete your code basically. So now let's go to that CAD program, and I'm just going to show you where I am with this project so far. So this is the root page. I have 3 sheets so far. I have the I have the microcontroller and power, and a battery interface, and battery cell interface that's used in LTC68. So far I'm testing. So far I'm testing the microcontroller. You know, I already created connections to test this microcontroller. I put the all the VBAT, VDD power to 3.3 volts, and I put the VDDA, that's for the analog, to 3.3 volts, but with the ferrite bead basically for filtering. I connected inverted reset pin through a capacitor, a ground. I'm not going to be using this reset button, so I just put it connected this way. And for the boot pin, so basically I connected the a switch here. This is a 2-position switch that basically initially it's connected to ground, and then you know, I can boot, for example, if I switch it to higher voltage. And as I mentioned, I added an external oscillator, as you see here, 60 megahertz, to exactly, I transferred all these pins that you did normally when you create, for example, this configuration here. What you want to do, you want to exactly transfer this pin. So for example, the oscillator is on pH 0 and pH 1. If you go back to the KiCad, you will have it on pH 0 and pH 1. So you basically transfer all these pins to your KiCad, and you know, for testing purpose right now, I just configured this microcontroller for testing purpose. I added the I2C, I added an LED basically for testing, and I will show you. Basically, I created the small program to basically test flashing this LED, and this is how it looks. And I added SPI and UART basically, and USB, as you see here. USB just to test specific functionality. Once I finish testing it and everything's good, I might add another protocol, CAN, for in case you want to use this BMS for electric cars. But at this time, I'm still thinking if I want to do it now or not. And then, basically this is what it comes to the microcontroller itself. Working on the battery interface, how cells going to be connected, and through that LTC6813 chip we're going to be using to connect that through terminal. And as I mentioned, that LTC68 chip, we're going to connect this to a microcontroller, and we're going to write the code. So for now, this is what I have. If you want to go ahead and produce this micro, so you can test it yourself, you can do that. I'm just going to share with you from my GitHub, my Gerber file, my bill of material, and pick and place, basically. And you can do that if you are interested. This is the PC board. Once you route all the connections, and I'm just going to go view 3D diagram. This is the PC board. There are a couple devices like this switch here is not connected. It's not on the bill material, but you can actually buy it and put it by yourself. And I didn't have these connectors here. I had to solder them myself. So let's see how actually you can order this from, if you are interested, from GLC PCB. This is the assembly house that I use to order my PCB. I don't do any advertising for them. I'm just showing you basically how you can order things. If you go to under order, click here, you add the Gerber file, and my Gerber file, it's in zipped, and I have it in my GitHub. If you upload this, and you have your PC board here uploaded. You can I just keep the default stuff, so you can choose the colors, the finish, whatever you want. If you want the component to be assembled, you don't want to assemble them yourself, you can just click on here, say next. Next again, and you can upload that BOM, bill of material, and pick and place file that I have in the GitHub, and then that's it. And then in hopefully less than 2 weeks, you should get your PC board and test them.